So in this video, I'm going to be deriving the equation for the lever rule and kind of talking about how it applies to flash calculations. So here I've redrawn the bubble and dew pressure plot. We have our Z value, which is the mole fraction of our first component in our feed. We also have the liquid mole or the vapor mole fraction and the liquid mole fraction of that first component on our graph. So I'm going to start deriving this equation. I'm going to write down two mass balance equations from video 3. If you remember, the first one was the total feed equals the total moles in our feed equals the total moles in our vapor phase plus the total moles in the liquid phase. And then we also have our other equation, which is the total moles of our first component in our feed is equal to the total moles of our first component in the vapor phase plus the moles of our first component in the liquid phase. So the next step in deriving this equation is plugging in, substituting the value for our total moles of feed in with the total moles of vapor plus the total moles of liquid. So I'm just going to substitute this into the equation. And we get this expression here. And the next thing I'm going to do is just multiply out this left side of the equation. So now if we look at this equation, we have a term for the total moles of vapor on both the left and right side of the equation, and the same thing for the total moles of liquid. There's a term on the left and right side of the equation. So I'm going to combine the like terms and then factor out the total moles of vapor and the total moles of liquid. And that will give us something that looks like this. And then from here, I'm going to solve for V over L, which will give us the ratio of the moles in the vapor phase to the moles in the liquid phase is the total moles of our first component in the feed subtracted from the total moles of that first component in the liquid phase over the total or the mole fractions of our vapor phase subtracted from the total mole fraction in our feed. So now we can see from here that this is the expression for the lever rule, and in the numerator over here, the z1 minus x1 value is this distance on our graph. It's this distance on our graph. And then the value in the denominator is the distance between our feed mole fraction and the vapor mole fraction on our graph. So we can actually use these distances if we plot this on graph paper and measure the distances here and here to calculate the ratio of our vapor moles to our liquid moles. This can also be used to kind of see the behavior as we raise the pressure in our flash drum. So I'm going to draw another plot over here to make it a little easier to see. Pressure on our y-axis and x1 and y1 on our x-axis. And then we have our two curves again. And if we start with our mole fraction in the feed of Z1, and we start at a pressure lower down here, as we increase the pressure, we're going to reach the dew point and create our first drop of liquid. And the composition for that liquid drop can be found over here with x1. And now as we continue to increase the pressure, we'll end up somewhere inside the two-phase envelope, and the distance between our z value and our y value will increase, but the distance between the z value and the x value will decrease. So this is why it's called the lever rule. As this distance increases, the other one's going to decrease, and it acts geometrically kind of like a lever. And then as we continue to increase the pressure, we'll reach a point somewhere up here, and we will create the first, or we'll start to become all liquid. And as you can see, the distance between our x1 value and our z1 value is 0. So if we come over to the equation, that indicates that the value for our vapor phase, the moles in our vapor phase, is 0. And so we will have all liquid at that point. So that's a little bit about how the lever rule applies to flash calculations.